in this lecture, we'll continue talking about terrestrial planets and cover the two outermost layers, the atmospheres and magnetospheres. And it turns out that magnetospheres occur not just on terrestrial planets, but in a variety of places in the cosmos, from galaxies to stars. So talking about them in some degree of detail will be important. And all of this is part of our grand tour of our solar system, where we're taking groups of objects that have similar properties, the inner terrestrial planets and the asteroids and the outer gas giant planets or Jovian planets, and then the comet-generating Oort cloud and Kuiper belt, and sequentially discussing them. So we are here and we will work our way outwards. So what we know so far is that terrestrial planets have what we call differentiated, which means the denser stuff over the course of the last 4 billion years has sunk to the center, and the fluffier material has made its way out to the edge. So the core of a terrestrial planet, and pictured here obviously is Earth, but this is true for everything from the Moon, which structurally we consider to be a terrestrial planet, to Venus. So there's a core, which is the heaviest material, iron and nickel, and then the mantle of medium density rocks, which could be molten, could be solid. That's the boundary in between those. The solid and liquid part is so-called lithosphere, and the crust. What will be important later is to mention the fact that the core of a terrestrial planet might also be partly molten and partly solid. So, for instance, the Earth has a molten portion of its core, molten metal, and spinning around on its axis, and this will be important to discuss later. And we also talked about the fact that a variety of influences can shape the surface of a terrestrial planet, and they come in two categories. They're either internal things that the planet does to itself, or external things that are happening from the space environment to the terrestrial planet. So internal influences would be volcanism, plate tectonics and seismic activity, like the motion of continental plates on top of this liquid portion of magma, and then weather in the form of both water and wind. So atmospheric and hydrological stuff. And then external influences include what's oh so dramatically pictured here, collision, but then also tidal influences. We've exerted a really profound tidal influence on the Moon and affected its behavior pretty strongly. And then space weather. And space weather is mostly for us the material that's being ejected from the sun, but it could also include the galactic environment when we talk about other structures later on in the course. So we categorize the terrestrial planets as geologically alive and geologically dead in terms of whether or not they have these internal and external influences. All terrestrial planets will be influenced by the external stuff, impactors and space weather, but only the geologically alive terrestrial planets will have volcanism and seismic activity, and this turns out to be because the thin lithosphere, the solid part of the outer edge of the planet, is so thin for the larger planets, so it's harder for them to cool down. It'll take longer, so they're still more molten. And this allows those processes to occur. So you have tectonic plates moving apart, and you get these stretch marks called graben. You also see a lot of volcanic activity as continental plates move apart. And then continental plates will smush together and form mountains. You see mountains on Mars and Venus as well as Earth. And in fact, you don't really think about the Moon as having such severe topography, but there are mountains that are comparably sized to the Himalayas on the Moon. So all of these were happening in the past on all of the terrestrial planets, but only for the larger ones, Venus and Earth, are these processes still continuing because they haven't cooled down yet. So if you wanted to potentially reanimate a terrestrial planet, unfortunately, you're left with hitting it with a large asteroid because the sources of this heat, again, I'm making the point that sunlight is not a significant source of heating up a terrestrial planet on the scales that we're talking about. Most of this is the primordial heat that was trapped when the terrestrial planet condensed out of a cloud of gas. So that's mostly the source of heat. There's some from differentiation. Again, the process of splitting the layers into the less dense and more dense layers. And radioactivity. There's radioactive material that gets incorporated into a planet, and as it decays, it heats the thing up, and that's significant. So what we're really honestly left with, if you wanted to, melt a lithosphere and get something uh, moving its continental plates around again would be this, which is elegantly described as accretion, aka hit with an asteroid. And you can see those processes both here. So these are lava beds on the moon, and these are the primordial lava beds from when the moon was first forming. This is the dark flat stuff, the so-called lunar maria. And then here you see this gigantic strike from some sort of impactor, asteroid or comet, and you see that it's actually melted its way all the way down, and there's a liquid pool of also lava inside of that. The lava plains on the moon showed ancient volcanic activity. You can see tectonic activity. These stretch marks are graben on Mars. You can also see some erosion. And even inside of large craters, you see these huge erosion structures. These are comparable to something that you see on Earth called the scablands in central Washington state, where cataclysmic floods have ripped across the landscape and made this particular form of scalloping. So this is evidence of obviously a water-rich ancient environment on Mars. And even now, to some extent, there's a teeny tiny amount of weathering that still occurs. So the remaining question that we haven't gotten to yet is, are all of these influences related to the lithosphere? So it makes pretty good sense that if you have a thin lithosphere, you should get more volcanism and plate tectonics. But the relationship to weather and erosion and atmosphere is a little bit more subtle. And if you think about it, you might start getting really suspicious because, you know, this is a artistic representation of potentially ancient Mars. And saying like, so wait a minute, the water disappeared and the atmosphere disappeared because the lithosphere got thicker? How on earth does that happen? But it turns out that, yeah, this is really what's going on. And to understand that, you need to know where atmospheres come from. So there are three processes that make an atmosphere, and one is just by volume or importance, by far easily the most important, and that's outgassing. But I've included the other two because they explain some of the features of Mars and the Moon. So outgassing is literally differentiation, where gases that used to be in the mantle have made their way out and ejected themselves through opening in the crust, usually a volcano, and replenish the atmosphere. Evaporation is a process where you might have some solid material, usually it's ice or dry ice, frozen carbon dioxide, and if you melt ice, you release the gases trapped inside of it. This is a lot less important than outgassing, and a little bit less efficient. And then finally, you have this process of making gas called surface ejection, and this completely explains the lunar atmosphere. The moon does in fact have an atmosphere. It's really, really thin. In fact, when the lunar landers, the Apollo astronauts took off on their little shuttle and they fired their rockets to get back to the Saturn V rocket that took them there, they managed to pollute with their little maneuvering rockets the entire lunar atmosphere for months. And what surface ejection is, the source of the lunar atmosphere, is basically solar wind, really energetic particles coming in and hitting a rock and ejecting an oxygen atom, for instance. So it's really just knocking the primordial components of an atmosphere like oxygen or carbon dioxide off of rocks, and then those things become gases. You can guess that this is a very inefficient way of making an atmosphere, but it is important, at least for the moon. So mostly we're talking about outgassing, and you cannot outgas without volcanism. So the more you outgas, the more material is spewed out. So here's a Yellowstone geyser, and you can see the stuff released from it. In fact, it also includes some really awful smelly stuff like sulfites. And then here is a large volcano. I think this is in eastern Russia, and you can see the huge amount of gas that's being released by it, as well as this dust and ash. But thousands, if not billions of tons per year of carbon dioxide principally and other gases are released by volcanoes on Earth. And what they're doing is they're replenishing the atmosphere. In fact, Venus is so good at this process, or at least was in the past, that Venus has had what's called a runaway greenhouse effect, where if you stripped off all of the atmosphere of Venus and just thought about the sunlight that's heating up its surface, Venus should be, without an atmosphere, 40 degrees below 0 Celsius. But its atmosphere, which allows visible light to pass but then traps it as infrared, has increase the temperature to about 470 degrees Celsius. And for people who are used to Fahrenheit, that's about 800 degrees Fahrenheit, which is enough to cook a pizza in like half a second on the surface. So in fact, on Earth, we're actually doing this in a very convoluted way, where when we pull stuff out of fossil fuel deposits and then we burn them, what we're really doing is a form of man-made outgassing. And so you can see the exhaust, and there's the carbon dioxide. So we're replenishing one part of the atmosphere. So I keep saying replenishing, which means obviously that we're losing atmosphere somehow as well. And in fact, any planet, anything that has an atmosphere in the neighborhood of our sun will be constantly losing its atmosphere and constantly needing it to be replenished. So by cutting off the outgassing, basically what happened to a planet like Mars is that the processes that strip off its atmosphere eventually won because nothing was replacing them. So you lose atmosphere by doing all of those things in reverse. So instead of melting ice caps to release atmosphere, if you condense stuff and freeze stuff, you can trap gases inside of them. So as you know, during the ice ages, there was less atmosphere because the glaciers would bind up those gases inside of the ice. And you can see two really big ice caps on Mars, and there's a lot of atmosphere trapped inside of that. It's actually dry ice or frozen CO2, it's not water ice. So secondly, you can lose atmosphere through chemical reactions, and the principal one that you know about is oxidization. So if you take a nail and you leave it outside for a couple of months, it gets exposed to weather and wind, and it'll rust. And when the nail rusts, what color does it turn? Oh, a nice rusty red. And if you look at Mars, the red planet, you'll see that the entire surface is a rusty red. So what this is there's tons of oxygen that's been trapped in the chemical reactions of oxidization on this planet. And then finally, you can lose atmosphere through either the gas just literally bouncing its way out of your gravitational influence, or more importantly, what's called solar wind stripping, where the solar wind, the material that's ejected from the sun's surface, really fast, really energetic, it just comes in and knocks a couple of molecules of your atmosphere off of the planet. And this is constantly happening. So we're actually pretty good at defending ourselves from a couple of these things, and we have an extra secret weapon, at least on Earth. But you can see that all of this stuff has happened on Mars. Certainly the condensation and freezing and the chemical reactions. It's also been solar wind stripped to a greater degree than it was in the past. And as volcanism stopped, so there's Olympus Mons, old volcano, it's not going to erupt anytime soon, Mars lost its atmosphere. And a lot of this has to do with the lithosphere, in fact. So, our secret weapon, as mentioned, against solar wind stripping is the other aspect of terrestrial planets, and that's the role of the molten core and its formation of a magnetic field, the so-called magnetosphere. So probably you're used to seeing permanent magnets and tracing the field lines, but maybe you did this science project as a kid where you take a battery and then you wrap a wire around a steel core. A nail would work pretty well for that too. And as the moving charges, the currents interface with the metal, what they do is they create a magnetic field. So here's if you didn't do that experiment, here's a really quick version of it for you. So this is a wire, and it's wrapped around a bunch of times. And then these are iron filings, which will just show you where the magnetic field is. And then you'll see really quickly as the person turns on the battery, you'll see the magnetic field suddenly appear. Oh, there it is. So the short story is that anytime you have electrons that are free to move and you spin them around, you should get a magnetic field. So anytime you have electrically conducting material and you spin it, you should get a magnetic field. And what'll happen over and over in this class is we'll find that there's something, maybe a star or the Jovian planets or a galaxy itself, those conditions will be met. There will be electric charges, usually free electrons, and they'll be spinning really quickly. Voila, magnetic field. So it turns out that Earth, which is spinning, and Earth, which has a molten core. So the fact that it's, excuse me, molten is really important because this allows you to get those electrically conducting free charges. So once you have free electrons which are able to move and you spin the planet, all of a sudden you get a magnetic field. And you can see the effect of our magnetic field, in fact, turns out to also save us from solar stripping. So this is a diagram of what happened in Mars's evolution, is that as well as its lithosphere becoming solid and thickening, the core itself went from being liquid to solid. So Mars used to have a core much like Earth's, which was liquid and convecting, and Mars is spinning. It's got, I think, like a 25-hour day, so comparable to Earth's. And it had a magnetic field, and the magnetic field would deflect the solar wind towards the poles and keep its atmosphere intact. Now Mars also has a solid core, no more magnetosphere, and the solar wind stripping has actually increased and ripped off the remainder of Mars's what used to be probably a rather thick atmosphere. In fact, you can see this. This is a simulated image of Earth in a solar weather event like a solar storm, and you can see these magnetic field lines reacting to and deflecting all the particles away from it. And everybody knows some effect of this. In fact, Earth's magnetic field deflecting particles towards its poles. And it's a very, very beautiful thing. We've probably seen pictures. If you've seen it in real life, you're very lucky. But this is basically the Aurora Borealis and the Aurora Australis. So the auroras are actually the solar wind, the energetic material from the sun, being caught up in the in Earth's magnetosphere, and as they spiral down towards Earth, they emit this like eerie blue, green, purple light. So here are just some beautiful images of the auroras, and I'll include some links in the slides. You should watch them in high def. A couple of them are from the International Space Station as they fly around and see the auroras. But this is, you should thank these if you see them, not only for being like really pretty, but for also protecting our atmosphere from being stripped off, solar stripping. Here's an image from space of one, and you can see the fact that there seems to be a ring of lines where the solar wind is interacting with this. Okay, so really quickly in this course, what's going to happen is we're going to lose the ability to go out and actually look at things. So we're on terrestrial planets and we have good access to a terrestrial planet, and some of the other ones just takes a little bit more work. But as we go out to stars and as we go out to galaxies, what becomes equally important is not the things that we know, but how we know them. And it's a fair question to ask, how do I know, for instance, that the core of Mercury is this big and its lithosphere is that big? I mean, imagine going to Mercury and digging a hole to verify this directly. Pretty difficult. So this will be part of what you guys do on exercise 5, but the answer to that particular question is that if you have something orbiting Mercury, you can figure out its mass, and then you can just look at its size, and from its size and its mass, you can determine the density of Mercury, and therefore we know, like, holy crap, it's really dense. It must be primarily metal and just not a lot of rock. And then secondly, another interesting way of determining information about the liquidity and solidity of our core. So how do I know that the core of Earth is part liquid? That information actually comes from earthquakes. And it turns out there are two types of earthquakes. There are the so-called compression waves, which are kind of like playing an accordion, and they're indicated here. And then there are the shaky waves, the S waves, which would be like grabbing a bed sheet and shaking it up and down, and you'll see waves transmitted through that. Well, it turns out you can make the compression, the pressure waves, travel through liquid. So the accordion-like pressure waves, they're basically sound waves, the same type of longitudinal waves that produce sound. They'll travel through liquid or solid, they don't care. But the shaky waves, so you can imagine taking a bed sheet and shaking it up and down to make waves. Imagine trying to do that with a bathtub full of water. So you can't grab it and you can't shake it, and those stop. So by listening to and watching earthquakes on the surface of Earth, we know some degree where the liquid part and where the solid part stop and start. So through ways like this, we actually have some degree of knowledge about what's going on the planets that we have visited, so we can observe earthquakes on them as well. And then for the other ones, some basic information about their size. And I will say that this is all really active and unsettled question, especially some of the paradoxes of early Mars. So we'll talk about this idea of a faint young sun, and the sun has gotten warmer and warmer and more powerful over the course of its lifetime. When Mars actually apparently had liquid ocean, the sun was 20 to 30% fainter, and that's a very difficult thing to resolve. So on the moon, in fact, we have tectonic observation data from that. So this is an astronaut setting up a seismometer on the moon, and there were a couple of them set up by the Apollo astronauts, and they really didn't expect to see much because the moon was considered to be completely terrestrial dead. But it turns out that there are lunar quakes, and they're much more interesting than people thought. So there are these surface lunar quakes, but then there are also some deep quakes, and there are unfortunately, the batteries on these things ran out before they took too much data, but they radically changed our idea of lunar geology. In fact, at that time, I don't think people even thought the moon had a core. And the idea that there are still things happening deep within the lunar mantle is still a little bit poorly understood and was surprising at the time. So this is the state-of-the-art picture of the moon, partly based on the tectonic activity. So this is the list of key terms and key ideas. Again, I would concentrate on the basics. I just want to include the stuff about early Mars and lunar moonquakes because it's still an active area of research. And it's a really interesting question, like how do we know some of this stuff? And the evidence gets less and less direct as we proceed in this course.